try that out. Okay, now I basically want to go into another interesting probability distribution, okay, that we call beta distribution. Okay, now let me tell you, we can derive the beta distribution from the gamma distribution. Okay, the origin of beta distribution is from gamma distribution. Okay, so when you take advanced, when you take, statistical, the theory of statistics, two, which I call 5102, of course, you're basically going to see that derivation, how we derived a beta distribution, okay, from the ratio of from gamma distribution in a way. Okay, but you know what? Before I go into that, I'm not going to tell you how we derive that, but I'm just going to walk you through the statistical property of a beta distribution, just like the same way I started the other time with, gamma function. Gamma function enable us to understand gamma distribution, and we also apply the idea of a gamma function, okay, in, exponential distribution. So right now, I also want to walk you through beta, you need to understand a beta function, okay? For you to be able to understand beta distribution, there's a difference between the two, okay? Beta function is different from beta distribution. Okay, now the beta function does not integrate to one, but beta distribution integrate to one, because a beta distribution is a probability distribution. Okay, so when we take a look at the beta function now, we have the integral definition, we have the non-integral definition. Okay, so what you're actually seeing now, give me 1 second. Okay, so this guy now is what we call integral definition of a beta function. Okay, that's what we call integral definition of a beta function. For instance, maybe you are actually giving this is 0 to 1, and you basically have x6, okay, into 1 minus x, okay. Maybe raised to power 4, okay, dx, okay, if you want to integrate this guy now, okay, it's actually going to take forever. Okay, so the fact that the state space from 0 to 1, okay, I can actually assume that, okay, you know what, this guy here is the same as b into 7, okay, 5. Take a look at that. Okay, I can actually see this as that. Take a look at that. So if this alpha minus 1. If this beta minus 1. That's why it says 6. Okay, add 1, 7, 4, add 1, 5. Okay, now if this is integral definition, this is going to be called the non-integral definition. Okay, okay, this is non-integral. Okay, so this is non-integral, okay, definition, okay. This is non-integral definition of a beta function. And why this is integral definition, okay, so this is integral, definition of a beta function. So all what we're just going to do, we're going to equate the integral definition with a non-integral definition. So if I want to do that, so definitely this guy here now is basically going to be gamma. So what is my alpha? It's going to be gamma 7, okay, gamma 5, okay, divided by gamma 12. Okay, and if you remember what we did the other time, okay, gamma k, okay, is actually k, okay, minus 1 factorial. Okay, now if I want to rewrite this guy now, oh my god, the gamma 7 is going to be 6 factorial. Okay, gamma 5 is going to be 4 factorial. Okay, and gamma 12 is going to be 11 factorial. Okay, and you know what, this guy can be easily be computed when you make use of your calculator. Okay, so I just try to tell you, both the integral definition of a beta function and the non-integral definition of a beta function. Okay, I need you to take note of that. And of course, in the beta function, or we still talk about gamma, alpha, gamma, beta, gamma, alpha plus beta. I need you to take note of that. Okay, now the next thing we want to talk about now is, can we have what we call, a way to have incomplete beta function. Okay, in a situation where what I basically want to do, maybe I want to derive the what is the CDF of a beta distribution. Okay, the other time I show you how to derive the CDF of a gamma distribution that was actually tractable, but for the beta distribution, that is basically going to lead to what I call incomplete beta function. But you know what? I need to take a look at this. This is what we call incomplete beta function. So which means if I basically want to find a CDF, okay, of a beta distribution, but don't forget the CDF, okay, it's basically going to be this guy. Okay, so which is going to be equal, I'm actually going to go from 0 to t. Okay, so when I go from 0 to t, okay, don't forget, I'm actually going to put the distribution. Okay, so I'm going to put the distribution, but what I'm going to get in the end, what you're going to see in the numerator of what I'm going to get is basically going to be this guy. Okay, that we call incomplete beta function. Okay, by the time we get to the beta distribution, now you're going to see that if I want to get a CDF, okay, the cumulative distribution function of beta distribution, okay, the idea of incomplete beta function is basically going to be used, and what makes that incomplete is because we're going from 0 not to 1. What make it, if you want to talk about complete, it's going to go from 0 to 1. But if you want to talk about incomplete, it's going to go from 0 to x, and the x here is going to be less than 1. We're not going to get up to 1. So that is what incomplete beta function is actually talking about. Okay, so I'm going to erase that. Then I'm going to, okay, it's just like what I said. When x equal to 1, it will coincide with a complete beta function. Like I said, okay, I expect my x here to be less than 1. Okay, s to be less than 1. When s is less than 1, it's actually going to be incomplete. Okay, so I want to go into this is what I talked about the other time. When you take a look at what I have now, oh my God, this guy that you are seeing right now is actually the CDF of a beta distribution. I'm going to say that again. This is CDF. How do I know that this is a CDF? In this CDF now, okay, what are you seeing? You're actually seeing the incomplete beta function, right? Okay, so this is more or less, if I want to write this guy now, okay, it's basically 0, the numerator, 0 to x, okay, and x raised to power alpha minus 1, okay, 1 minus x, okay, because of the fact that because of x, yeah, what we used to do. Give me 1 second. I'm actually gonna erase this and trying to make it t. Okay, so here I'm actually gonna write t, okay, alpha minus 1, okay, 1 minus t, okay, beta minus 1, okay, the t. Okay, so if I take you back to what we did the other time, you can see it's right here, right? Okay, so if you take a look at the denominator is going to be all of that, but except that it's going to be complete. It's going to terminate at 1, and I'm actually going to have, okay, this guy here, okay, 1 minus t, okay, raised to power beta, okay, minus 1, okay, dt. Okay, so what you are seeing now is the same as the probability, okay, of x, okay, less or equal to s, okay, that we actually call an uppercase F, okay, which is going to be the CDF of a of a beta, distribution. Okay, take a look at all of that. Okay, so the property, you can actually prove a property situation where ix equal to this. Okay, when the x equal to 0, you know what I mean? Okay, when the x equal to 0 is more or less like you're putting 0 here, automatically the numerator is going to be equal to 0, and that's why you have that down. Okay, what if we put 1? Okay, if I put 1 here, okay, the whole of this is going to be the same thing as this. That's going to be 1. Okay, and we can also say that's a situation whereby if I have ix of alpha beta, it can be equal to 1 minus, if you take a look at this guy now, okay, it's just talking about switching the position, okay, switching the position of alpha and beta. Here t is the one carrying alpha minus 1. If you change that to beta minus 1 and you take this one to alpha minus 1, this is exactly what you have. Okay, I need you to take note of that, and this can also be proved, so you can also try that out. Okay, so let me tell you this. If you basically want to try this guy out, okay, so what you're trying to say is where you have your alpha, you want to put alpha plus 1, okay, and at the end of the day, you're basically going to end up in this guy. Okay, so I'm going to leave you, for that, okay, to that, so you can try that. Okay, so this is the beta distribution now. Okay, this beta distribution is actually used to model proportion. Okay, something in the range of 0 to 1. If you want to talk about customer satisfaction, okay, it is not all your customers that will be satisfied with your product or service. Okay, we're gonna have a situation whereby the proportion of those who actually get satisfied with your service or product is basically going to be in the interval 0, 1. Okay, it can never be 0 and it can never be 1, but it's going to lies in the interval. What I'm trying to say, 100% of your customers, of course, will not get satisfied with your product, and 0% will not get satisfied with your product. Okay, going to be something in the region. Okay, now if I want to model proportion now, if I want to model a random variable in the range of 0 to 1, okay, and if I want to conduct any statistical inference on that, then I need a beta distribution. Okay, and this is the beta distribution now. Okay, this is the beta distribution. Okay, and of course, when you have a beta distribution, the mean and variance of a beta distribution actually exists. Okay, so like I said, the mean and variance of the beta distribution exists. This is the mean, okay, and this is actually the variance. Okay, and of course we can actually prove that guy out. Okay, but what I'm going to first do with you now is a situation whereby how can we actually investigate that this integrate to 1. Okay, if you want to integrate, okay, over the range, okay, 0, 1. Okay, so if you write all of these, okay, I need you to take note of something now. Okay, if this is this, okay, and 1 minus x, okay, or raised to power, or beta, okay, minus 1, okay, ds, okay, and everything now is equal to everything, divided by b alpha beta. Okay, if you look at the numerator, you're going to see that numerator is a complete beta function, go from 0 to 1. Okay, it is also the same thing as this guy. Okay, so if you want to go back to what I did the other time, if you have this guy now, okay, when your x equal to 1, what happened? That give you 1, right? Take a look at that. Okay, so the fact that give you 1, that shows that is a valid, PDF. And another thing we can do, we can actually try to see how can we derive the mean. Okay, so expected value of x, okay, expected value of x, if you really want to do that, okay, based on the property, okay, don't forget x, f of x, and the f of x is 0 dx, right? So which is x raised to power alpha minus 1, okay, 1 minus x, okay, raised to power beta, okay, minus 1, okay, dx, okay, and you're going to divide everything by b, okay, alpha, okay, beta, okay. Now if you combine this with this, you know what you're going to get? Okay, this one, like you're going to get x raised to power alpha, right? Okay, I don't want to waste my time. I'm actually going to erase, okay, this guy now. Okay, when I do that, okay, so this is good, going to be x raised to power alpha, okay, and when you take a look at this, I can actually use the idea of a gamma, of a beta function. Okay, now when you take a look at this, the numerator here can actually be written as b into what is this, alpha. So you're going to do alpha plus 1, comma, then add 1 to this. That's going to be beta, okay, or divided by b of alpha comma beta. Okay, so when you take a look at this now, I can now apply the knowledge of incomplete beta function. Okay, so when you take a look at this guy now, okay, it's going to be, let me write here. So if you take a look at this guy now, it's going to be, okay, I think I'm going to do something now. I'm going to clean up so that I don't really confuse. Okay, so when I clean that guy now, okay, when I clean that guy now, okay, so what I'm actually trying to tell the world is expected value of x is going to be equal. So here now, I'm actually going to have gamma alpha plus 1, okay, or gamma beta, okay, divided the gamma of the addition of alpha plus beta, okay, plus beta plus 1, okay, now divided by this. Okay, so divided by this, I can, if I change it to multiplication and you take a look at this, it's going to be gamma alpha plus, beta, okay, divided by gamma alpha, okay, gamma beta, okay. So the gamma this is going to cancel that, okay. And when you take a look at, let me clean my board, so that you're going to clean this guy now so that I can have a space. Okay, I want to have a space. Okay, now this guy now can actually be written as, if you take a look at this, it's going to be alpha gamma alpha, okay, divided, okay, this guy can obey that guy. I'm actually going to have alpha plus 1, okay, into gamma alpha plus beta, okay. I mean, this guy now multiply by, gamma alpha plus beta, okay, divided by gamma alpha. Okay, this actually cancel that. The gamma alpha cancel gamma alpha. What do I have left? I have alpha over alpha plus beta, which is actually this guy. Okay, you can try that of the variance. Okay, what you're going to do. If you want to try that of the variance, of course, you know that the variance of phase is basically, expected value of s squared, okay, minus expected value of x, okay, all squared, okay. You've already gotten the expected value of s. All what you just need to do is to get the expected value of s squared, okay. In the end, okay, when you simplify, of course, that is what you're going to get, for the variance. Okay, so if that is what you get for the variance, okay, of course, I think I just proved this now. Just proved that mean equal to that. And of course, it's very interesting to tell you that when alpha equal to 1 and beta equal to 1, it's actually going to take you back into uniform distribution. Okay, when alpha equal to 1 and beta equal to 1, okay, you're actually going to go into uniform distribution. And in that situation, the mean is going to be equal to half when you start plugging in what is your alpha, and your variance is basically going to be equal to what I have now. Of course, you remember in uniform distribution, right? In uniform distribution, what we actually, you remember that the mean in a uniform, was actually what? Okay, you remember in the uniform that we have A plus B over 2. Okay, when you plug in 1, 1. Okay, so what I'm just trying to, make you understand is because we can also have situation, even though I know the continuous unit form that I taught you is actually f of x, okay, which was equal to 1 over, b minus a. If you remember what we did about the continuous or uniform, it's actually that. But let me tell you, okay, uniform distribution can also be equal to 1 instead of equal to 1 over b minus a. Okay, we can have, if f of s, okay, is actually equal to 1, that's a uniform distribution as well. So I'm going to tell you more about this as we go on. So what I'm trying to tell you now, if you basically go back, okay, if you go back here now and you plug in 1, 1, okay, s raised to power, you're basically going to have s raised to power 0, like if you plug in 1 here, you plug in 1 here, and 1, 1. So you're basically going to have 1 over b of 1 and 1. Let's take a look at what we're going to get. Okay, 1 divided is going to be gamma 1, okay, gamma 1 divided by gamma 2, right? If you actually want to express what I have here, and which is going to be, because of the reciprocal, you're going to have, let me write that. So here, this is going to be gamma 2, okay, divided by gamma 1 and gamma 1, and, gamma 2 is actually 1 factorial, and gamma 1 is 0 factorial, is 0 factorial, and 0 factorial is 1 factorial is 1. So that will give you f of s equal to 1. So f of s equal to 1 is also uniform distribution. I'm going to explain more, okay, as time goes on. Okay, now, there's an exercise that I left for you here. Okay, if you take a look at what you are seeing here, this is give me 1 second. If you take a look at what I have, you're going to see that this is looking like a beta distribution. You can see y in the 0, 1. Okay, what if I say find the values of c that make that? So if I were you, what they are trying to tell you is you basically, going to use you can use the idea of a beta distribution, the y, everything now must be equal to 1, okay, over the 0 to 1. Okay, or what you're going to do, you can go direct integrating that, find, solve for c, and you can even use the idea of a gamma function, of a beta function. Oh my god, if you want to use the idea of a beta function, do you know that my c, okay, let me if you break it, see out. So it's going to be 1 divided by 0 to 1, okay, y squared 1 minus y raised to power 4, the y, okay. And if you take a look at this, you can see that that is basically, oh my God, that is basically going to be a beta function that I'm actually going to write 1 into b, okay, into, if you take a look at this, if I basically want to know the parameter, because what I have here, okay, it's more or less like equating that, okay, if I have, alpha minus 1 equal to 2, okay, the alpha is going to be 3, so it means that's going to be 3, and automatically this guy here is basically going to be 5. Okay, now you can use the idea of a non-integral definition now of a beta function, to finish that off. Okay, so these are other questions, that you can attempt, or maybe in the next class, I'm actually going to shed more light on all of this. Okay, so that is where I'm actually, gonna stop, okay, today until on Monday, that I'm actually gonna come your way again. Make sure you stay safe and have a very good day. Okay, so goodbye for now, everyone.